Welcome everyone to the next video lecture. In this video lecture, we will be discussing about the reactions of aldehydes and ketones. So now the reactions of aldehydes and ketones are divided into several parts. Okay, so first part we will be discussing about the nucleophilic addition of aldehydes and ketones. Then we will be talking about the oxidation and reduction reactions of aldehydes and ketones. Then some miscellaneous reactions, and if you want me to cover the topics regarding those entrance exams, there are many reactions covering syllabus for the entrance exams, and if you want to cover me those things, please mention in the comments below. So let's begin. First of all, I would like to thank biomolecule classes for giving me the opportunity to teach you guys. Thank you. So let's begin. First, we will be discussing about the nucleophilic addition reactions. The first list, there is addition of hydrogen cyanide. Now, both aldehydes and ketones react with hydrogen cyanide to form addition products known as cyanohydrate. As you can see here, this is hydrogen cyanide, HCN. So if you look closely, then we can see here that cyanide in hydrogen cyanide, this cyanide group, the carbon in the cyanide group bears a negative charge and the hydrogen bears a positive charge. As you know earlier that in carbonyl group, carbon atoms bears a positive charge and oxygen bears a negative charge. And in the previous lecture, I have shown you the ionic addition, that is, negative will go and attack the positive center in both the cases. Okay, so here we are getting that oxygen will add up hydrogen atom, whereas the carbonyl carbon will add up the cyanide group. So in the final molecule, you can see that oxygen is adding the hydrogen and carbon adding the cyanide group. So this molecule is known as cyanohydrate. So if you look into the example of the ketone, similar thing is going on. Okay, and we are getting, sorry, this one will be CH3, not hydrogen. This one is also that two groups are there. If we break this one, okay, that carbon will add cyanide and oxygen will take up the proton. Okay, so the reaction with pure hydrogen cyanide is very slow. Therefore, the reaction is carried out in the presence of a base which acts as a catalyst. Okay, if you look into the reaction, this hydrogen cyanide molecule will not dissociate to hydrogen, will not dissociate into a proton, that is H plus, and a cyanide ion. So what we will do is we'll give some base here. It may be NaOH, it may be KOH. Okay, so in presence of a base, the base removes the proton from HCl and readily produces cyanide ions, making the reaction faster. So if we give base here, say this one OH is a base, so what it will do is it will abstract the proton from the hydrogen cyanide molecule, that is, it will abstract H plus. Okay, so here OH minus plus H plus will give you water, and the remaining is the cyanide ion. Now you can see here carbonyl group, carbon bears a delta positive charge and oxygen bears a delta negative charge. So opposite poles attract each other. Cyanide, being negatively charged, will attack the carbonyl carbon, and these pi bonds will shift over oxygen atom due to its electronegativity. As oxygen is more electronegative than carbon, so it will handle the pi electrons much more efficiently than carbon atoms. So the pi electrons will go over oxygen atom. So we are getting a tetrahedral intermediate as discussed in the previous class that we'll be getting an alkoxide intermediate in nucleophilic addition then protonation reaction. So this one is the example of nucleophilic addition then protonation. So first nucleophiles adds to the carbonyl carbon, and then the alkoxide intermediate forms. Later protonation of the alkoxide intermediate from the solvent molecules give you the final product. Here it is cyanohydrin. So now you can see that now cyanohydrin, okay, it can be used to prepare many organic compounds. So it is a very valuable compound. This cyanohydrin molecule, if you hydrolyze this one, okay, with water, this cyanohydrin molecule, if we hydrolyze it with water, what we will get is lactic acid, that is alpha hydroxypropanenitrile acid. What it does is cyanide group in presence of water hydrolyzes to carboxylic acids. You will be learning this reaction in the preparation of carboxylic acids, that how the hydrolysis of cyanide molecule will lead over to carboxylic group. Okay, so here cyanide molecule, if we hydrolyze it, this will give us carboxylic acid. Now further heating it with H2SO4 will give us acrylic acid. Now what happens is that this CH3, okay, from here one proton makes double bond and OH leaves. So in presence, if we heat this lactic acid in H2SO4, then we will get acrylic acid along with some water molecules. Here what is happening is that water molecule is going out. This CH3 molecule contains protons, so the proton will leave along with hydroxy group, forming a double bond and water molecule. Okay, now if we treat this cyanohydrin molecule with ammonia, then what it will do is it will exchange with the hydroxy group. Okay, if we see here that this ammonia molecule, it will exchange with the hydroxy group. See here in the product, okay, all the three groups, that is methyl, hydrogen and cyanide, are intact, but the hydroxy group is exchanged with amine group, NH2 group. Okay, that is one hydrogen from ammonia, and this OH will leave to give us this water, and ammonia's NH2 will go and attack that one. Okay, now further hydrolysis of this one, what you will get is that this cyanide group will further get hydrolyzed to carboxylic acid, and the final molecule we are getting is alanine, that is an amino acid, and previously we were getting an alpha beta unsaturated acid, that is acrylic acid, and this acid is used in many organic synthesis, so it is a very valuable acid, and this one is a very valuable amino acid. It is present in our body. Okay, so now moving on the further reactions, that if we treat cyanohydrin, okay, if we reduce this cyanohydrin, so what we will get is that if we reduce it with lithium aluminum hydride, this cyanide group Cn, okay, C triple bond N, if we reduce this one, what we will get is CH2 bond NH2. Now here look, for one bond we are adding two hydrogen atoms in reduction, okay, for one single bond. Okay, since here three bonds are present and here it is one bond, so we are breaking two bonds, so we will be adding four new hydrogen atoms. per bond 2 hydrogen atoms. Okay, so there is 2 bond, so we will be adding 4 hydrogen atoms. 2 goes for this carbon and 2 goes for this nitrogen atom. So in cyanohydrin molecule, if we reduce it with lithium aluminum hydride, so here we see that the cyanide group changes to CH2NH2. That is two bonds we are reducing. That is triple bond to single bond we are reducing. That means we are reducing 2 bonds. So per atom, 2 hydrogen, per single bond 2 hydrogen atoms are being added. Since here 2 single bonds are being reduced, so 4 hydrogen atoms for two hydrogen atoms for this carbon and 2 hydrogen atoms for this nitrogen atom. Okay. Similarly, cyanohydrin formation of benzaldehydes gives different products under different reaction conditions. Means that if we exchange this methyl molecule with a phenyl group, we get a benzaldehyde. And further treatment of benzaldehyde with hydrogen cyanide in presence of a base, we get a cyanohydrin which will undergo these reactions. Okay, so just replace the methyl molecule with a phenyl group, and treat under the same reaction conditions, you will get a similar kind of product where this methyl group will be replaced by a phenyl group. Now, so this won't you won't get any acrylic acid here, because in phenyl the ipso carbon does not possess any hydrogen atom. Okay, you will get up to this acid. Okay, now the carbonyl atom, if you treat it with hydrogen cyanide, it will form cyanohydrin. So here's you see that if you partially hydrolyze this one, we will get alpha hydroxyamide. Okay, will give stoichiometric amount of water. Okay, we have to maintain some ratio according to our reaction conditions. We will be maintaining some ratio and we'll add water maintaining that ratio. If we maintain that one, we'll achieve partial hydrolysis, and that will lead to alpha hydroxyamide, in which the cyanide group is converted to CONH2 group. Okay, CONH2, not to carboxylic acid. Okay, if we completely hydrolyze cyanohydrin, then we will get this acid, that is alpha hydroxy acid. Okay, and if we reduce this one with nickel hydrogen or lithium aluminum hydride, we will be getting amino alcohol. As you can see here that this one 3-amino propanenitrile amino alcohol we are getting, we are reducing this one, and here we are completely hydrolyzing, so we are ending up with acid. Okay, so partial hydrolysis we will get CONH2, complete hydrolysis we will get COOH, that is carboxylic acid, and reduction will give us CH2NH2. So to achieve amide, you have to partially hydrolyze the cyanide group. Next, moving on to optical isomerism in 2-hydroxypropanenitrile. This topic is very important for your entrance exam, as questions come from here, that MCQ questions. Okay, so 2-hydroxypropanenitrile, so CH3, this one hydrogen, this one cyanide, and this one hydroxy group. So this is your 2-hydroxypropanenitrile. Okay, so if you want to name this compound, how will you be naming this? What is the nomenclature of this compound? Okay, see here, cyanide, it's a functional group and OH will act as a substituent. So functional group always get preference over substituents. Okay, so here numbering, this is the long chain carbon atom. Okay, long chain carbon atom, and the numbering will start from this cyanide group 1, 2, and this 3. Okay, so in carbon number 2 we are getting 1 hydroxy substituent. So 2 hydroxy, since 3 carbon is there, propane and 1 nitrile group in first position, so nitrile. Okay, that CN group is nitrile group. Okay, so now moving on to isomerism, as we were talking about. Pay attention, this one is very important for your entrance exam, always comes in the entrance exam. So optical isomerism occurs in compounds which have 4 different groups attached to a single carbon atom. Okay, so here we can see that this compound can show optical isomerism as the 4 atoms bonded to the carbon are different. Okay, in this case the product molecule contains CH3, CN, hydrogen and hydroxy, all attached to the central carbon atom. The reason for the formation of equal amounts of 2 isomers lies in the way that ethanol gets attacked. Okay, so you can see here, if you want to form this cyanohydrin, what is the reaction? So you break this hydrogen and cyanide from here from this cyanohydrin. Okay, you just break this one. So what if you remove this hydrogen and cyanide? So what you will get is ethanol. Okay, so you see that ethanol, this one, if you react it with hydrogen cyanide, we will be ending up with this 2-hydroxypropanenitrile. Okay, this cyanohydrin. So ethanol is a planar molecule. As you can see, as you know that carbonyl group is a trigonal planar group. So ethanol of course will be a planar molecule. An attack by cyanide ion will either be from above the plane of the molecule or from below. Since you see here, if you consider this as a plane of paper, so attacking of this carbonyl carbon can occur from above the plane or below the plane. Okay, I have shown this one in my previous lecture, how these carbonyl groups get attacks from above the plane and from below the plane. Okay, and there is an equal chance of happening either. Okay, as you can see here in this one, this ethanol molecule, if you consider this one as a plane, okay, see here, attack can be from here, that is from upwards, or from here, that is downwards. So attack from above will lead to one of the 2 isomers, and attack from below will lead to other. So in optical isomerism, I told you about isomerism. Okay, while I was discussing about the isomerism in aldehydes and ketones, I was telling about the isomerism. What are isomers? Isomers are the compounds or molecules having same molecular formula but different groups or different atoms arranged among themselves. Okay, so in this one we are getting 2 isomers, so attack will leave. So here attack from above will leave first isomer, and from below we will get second isomer. Okay, now we have to identify which one is which. Okay, so if attack is from above the plane of the molecule, existing group gets forced down away from the approaching cyanide ion. See, cyanide ion, it has a negative charge. All these bonds will have also negative charge. If this cyanide ions comes from upward directions, all the groups in the plane will be pushed downwards. Okay, see, this one was planar and now this one is a tetrahedral intermediate. So in tetrahedron you see that one bond is above and 3 others like this. Okay, this is the tetrahedron. Okay, this one forms a pyramidal base and this one is above the plane. Okay, it's just another view of it. This is just another viewing angle of tetrahedron. Okay, so cyanide ion will be here in the topmost position and these 3 groups in the base. that is in the apex position of a pyramid it will be cyanide, and in the pyramidal base position the three groups, that is methyl, hydrogen and hydroxy. Now if the attack occurs from below the plane, if cyanide molecules attacks the carbonyl carbon from below, so this all these three molecules will move upwards to maintain the tetrahedron position. Okay, now we take this second molecule here. This one is the second molecule, cyanide is below the plane. Okay, and now we simply rotate it so that the cyanide group comes to the top position. Okay, so here this one we are getting after rotation of the second attack, that is when cyanide ions attacks the carbonyl carbon from below the plane, the final product we are getting, we are just simply rotating this one. So now we will take this compound and compare it with this compound from the first one. Okay, so now compare the molecule formed by attack from above. See here, in this one hydroxy group is in left position, and in this one hydroxy group is in right position. I'll just clear all this mess. See, in this one red hydroxy group, here it is in right hand side position, attack from above the plane, and from below the plane hydroxy, after this rotation the hydroxy ends up in left position. Okay, so this one is from the second attack and this one is from the first attack. So look at these two molecules, they aren't the same. Here you can see that the cyanide and hydrogen, okay, cyanide and hydrogen both are in the same position, but if you look closely, then hydroxy and methyl group, this green portion and red portion, red one is hydroxy, so red hydroxy and green methyl group are reversed. Okay, so basically you can see here these two compounds, okay, have the same molecular formula but their arrangements are different. Okay, here in the first attack hydroxy is towards the right hand side and methyl is in the left hand side, whereas in the second attack the thing is reversed. Okay, so these two are isomers, this 1 and 2, that is the first molecule and the second molecule, the cyanohydrins are two isomers, and the relationship they share is that they are non-superimposable mirror images. See here, if we place a mirror, okay, if we place a mirror in front of the first molecule, you can see here the mirror image formed will be 2, that is cyanide to cyanide, hydroxy to hydroxy. Since hydroxy is near to the mirror as compared to methyl, so in the product also, in the reflection also, that is in the second one, we will get hydroxy ending up nearer to the mirror as compared with the methyl group. Now if we want to take this molecule, second molecule, and if we want to superimpose this second molecule over the first, then we can see that the second molecule is not superimposable on the first molecule. Okay, so the relationship they share is non-superimposable, and of course they are mirror images of each other, so non-superimposable mirror images of each other. Okay, so and because there is an equal chance of the attack coming from above and below the plane, we will get an equal amounts of two isomers. So we will be getting 50% of this molecule and another 50% of this molecule. Okay, now you are clear. Since attack can happen from either side, that is from above the plane and from below the plane with equal chances, so we will be getting 50% of the first attack and 50% from the second attack. Okay, so now if we look into the optical isomerism, okay, what is optical isomerism? If what is optical activity? Okay, first of all, if we place a compound and pass sodium d light over that compound, so after passing the light over that compound, what you will see that the light gets reflected to some angle, certain angle. Okay, see here, if we consider this one, okay, and if we pass through this line only 0 degree angle, if we place one compound and this is my 0 degree, okay, we can see that here it is a 360 degree circle. Okay, you can see that the final light coming is deviated within some angle, with some angles. Okay, so that is known as optical activity, to deviate the light by certain angles. That is the characteristic property of a molecule. So now if you see that, and another characteristic property is that if a molecule has a non-superimposable mirror image, okay, then what its mirror image will do is that, suppose this molecule number 1, okay, it deviates the light by, suppose, 10 degree. Okay, since molecule number 2 is a non-superimposable mirror image, okay, suppose this one, molecule number 1 deviates by plus 10 degree, okay, plus 10, remember this one, and now molecule number 2 have the same groups, okay, cyanide, methyl, hydrogen and hydroxy, okay, same groups, but the thing is they are reversed, that is hydroxy and methyl group. So what it will do is, the non-superimposable mirror image part will deviate the light by same amount, that is by 10 degree, but in opposite direction. That is, here it was plus, so here it will be negative 10 degree. So ultimately what you will get is, if one compound deviates the light by 10 degree, its mirror image will deviate the light by the same amount but in a opposite direction. So if a compound has 50% mixture of both 1 and 2, so one will deviate the light by 10 degree and the second molecule will deviate the same amount by the same amount but in a reverse direction. So overall, plus 10 degree minus 10 degree. Okay, so if we sum it out, we will get 0 degree. Okay, that is, the molecule will not deviate any light. Okay, and this type of mixture is termed as racemic mixture, where both non-superimposable mirror images are present in equal amounts. Okay, in equal amount, this is mandatory. They should be in equal amount. Okay, means 50-50%. So 50-50 mixture of non-superimposable mirror images are known as racemic mixture. Okay, so all aldehyde will form a racemic mixture in this way. Okay, and unsymmetrical ketones will as well. So all aldehydes will form this racemic mixture. And unsymmetrical ketones, why not symmetrical? Because in symmetrical, okay, these two groups are same, but to be optically isomer active, means optically active, we have to have different groups around the tetrahedral carbon. Okay, means around this carbonyl carbon, we should have different groups to be optically active, not same groups. If symmetrical ketone, then this carbonyl carbon will have same group. So here it is worth noting that unsymmetrical ketones will give this racemic mixture, unsymmetrical ketone. Okay, so in question it may come that they will give one molecule, means they will ask you that which one forms a racemic mixture among this cyanohydrin or among this cyanohydrin reaction. They will give you 4 options, among which you have to choose one, and they will be asking which one forms a racemic mixture. So you got the idea of racemic mixture, what is it and how it forms, and you get that all aldehydes will form racemic mixture and unsymmetrical ketones as well. Okay. Now moving on to addition of sodium bisulphite. Both aldehydes and ketones form crystalline addition compounds called bisulphite adducts. What are adducts? The addition compounds, after addition the compounds we are getting are termed as adducts. Means we are having all the things after addition in the substrate. Okay. So these are crystalline addition compounds called bisulphite adducts when treated with saturated solution of sodium bisulphite. So if we treat carbonyl compounds with saturated sodium bisulphite, then you will get these crystalline addition compounds which are known as bisulphite adducts. Okay, this reaction is utilized for the separation of carbonyl compounds from non-carbonyl compounds. Well, that's a remarkable property of this reaction, that you can separate carbonyl compounds. So how is it done? Okay, so if you have a mixture of carbonyl compounds and a non-carbonyl compounds, okay, so this sodium bisulphite, saturated solution of sodium bisulphite, if we react with that mixture, so it will react with the carbonyl groups, that is the carbonyl compounds, to give a bisulphite compound, that is bisulphite adduct. So it will react only with the carbonyl compound to give this bisulphite adduct, which on further hydrolysis will give you the carbonyl compounds back. That is, you regain your carbonyl compounds. So what you have left is a separated mixture. See here, non-carbonyl compound plus carbonyl compound. You have given this mixture. You just add sodium sulfite bisulphite. So the carbonyl compounds will react with that sodium bisulphite and give you an adduct. So you separate that adduct. Since it is crystalline, so you can easily take it out. Okay, since it is crystalline solid, so you can take easily, okay, from the reaction mixture. Then you treat it with normal acids or base. You just hydrolyze it, you will get your carbonyl compounds back. Okay, so how does the mechanism goes? So this is your sodium bisulphite. As you can see, sulfur having lone pair of electrons will attack the carbonyl carbon, and this will open up. Now this O minus, after this oxygen will gain a negative charge, this O minus will take proton from this hydroxy group. From this hydroxy group it will take the proton, okay, and this bond will cleave and go into making sulfur oxygen double bond. Okay, this one, and this one is the crystalline solid. Okay, this one, and another mechanism, another thing, this one, let me just clear this one. Okay, see here. Okay, this one, sodium plus HSO3 minus, it will go and attack the carbonyl carbon. You will get ONA and this SO3H. Okay, and then proton transfer occurs here, and you are getting with this compound. Okay, that is the crystalline solid compounds you are getting. Now this was this mechanism is in your books, so you will be following this one. I am using this mechanism just to show how the attack is going on. Okay, this attack from the sulfur to carbonyl oxygen. Now as the reaction is reversible, the addition products can be decomposed by mineral acids or aqueous alkalis. So here you can see that in this mechanism, all the steps are reversible. See here, this one is reversible. Just let me clear. So you can see here that this step is reversible step and this step is also reversible step. Okay, so as the reactions is reversible, the addition products can be decomposed by mineral acids or aqueous alkalis to give back the original aldehyde or ketone. So therefore the reaction can be used in the purification and separation of aldehydes and ketones from other non-carbonyl compounds. So you can purify and separate from the mixture. See, these are the adduct. Okay, so if you treat it with HCl, that is mineral acid, you are getting this ketone, that is acetone, and the same adduct if we treat it with NaOH, sodium hydroxide, you are getting the same ketone. Here the side products are different, so you do not have to take into consideration these side products. Our main original compound is this ketone. Okay, now reaction with Grignard reagent. So you have a glimpse of this reaction in that reactivity of aldehydes and ketones, I guess, in which you have seen that what ketones reacts with Grignard reagent to form tertiary alcohol. Okay, sorry, in the preparation part, why we cannot use Grignard reagent, why we have to use this dialkyl cuprates, okay, or dialkyl cadmium reagents instead of Grignard reagent. Why you use? You get a glimpse over that the carbonyl compound formed in the reaction will further get reacted with Grignard reagent to form alcohols. Okay, so here now we will discuss that in details. Okay, so reaction with Grignard reagent. Aldehydes and ketones react with Grignard reagents to form addition products which after hydrolysis gives alcohols. So you will be ending up with alcohol. So formaldehyde will give you primary alcohol. Other aldehydes except formaldehyde will give you secondary alcohol, while ketone will always give you tertiary alcohol. Okay, so this reaction will always be done in presence of dry ether. This is a very dry reaction. As you know, I have previously told you guys that Grignard reagent is very reactive. With water it will react to give you alkane. Okay, so you see that here, don't see this arrow, just these are the addition products. Okay, R minus, okay, negative charge, it will go and attack positive charge, then this will open up to oxygen and oxygen will thus combine with magnesium halide. Okay, remember always to use the proper arrows. Here the arrows are showing that this portion, this R portion will go over to carbon, and this magnesium halide portion, will go over to oxygen atom. They are indicating this only, but for a reaction you have to use proper arrows, negative to positive always. Okay, so we are getting R with carbon and magnesium halide with oxygen. So for the hydrolysis, this will remove this magnesium halide and give you OH. So you are getting alcohol and magnesium hydroxyhalides. Okay, so that is, you see here, okay, this OMgX bond. Okay, and this is the water molecule HOH, means H2O. You just leave here. Okay, so you are getting alcohol OH and MgOXH, that is Mg here X and another OX. Since magnesium has a valency of 2, so it will coordinate with OX and X. Okay, so now here you see that this is the simple example, acetone, and this is ethyl magnesium chloride, ethyl group, this one. So this Grignard reagent is ethyl magnesium chloride. So this carbon will bear a negative charge, it will simply go and attack the positive carbonyl carbon, and this will open up, this will take the remaining magnesium halide portion, as you can see in the here in the intermediate. Further hydrolysis, this OMgCl will get converted to OH. Okay. So here you see this is the Grignard reagent. This one is formaldehyde, and second step is hydrolysis. So formaldehyde giving you primary halide, other than formaldehyde gives you a secondary halide, and ketone gives you a tertiary. Oh, I'm sorry, extremely sorry. Formaldehyde gives you primary alcohol, not halide, primary alcohol. This other aldehydes except formaldehyde gives you secondary alcohol. This one is primary, this one is secondary, and ketones after hydrolysis will give you a tertiary alcohol. These are few examples you can see here. This one is the primary alcohol, one example. You can see formaldehyde here reacting with phenyl magnesium bromide. So you are getting this intermediate further hydrolysis giving you benzyl alcohol, that is a primary alcohol. Second is that acetaldehyde. Okay, here there is a CH3 group. Excuse me, and because of this CH3 group only you are getting here secondary alcohol. Okay, this look here, this CH2 means this hydrogens. Okay, this hydrogens, formaldehyde contains two hydrogens, so CH2. Okay, here acetaldehyde contains one hydrogen, so only one hydrogen in the product. So because of these two hydrogens you are getting 1 degree alcohol, that is primary alcohol. Here because one hydrogen is present and the rest two groups are substituted groups, so you are getting secondary alcohol. Now whereas in ketone you see that this carbonyl carbon does not contain any hydrogen atom, so you are getting a tertiary alcohol in the product, as this carbon, this one was the tertiary carbon, this carbon does not contains any hydrogen atom, so hydrogen atom is not there. Okay, so you can see here that this one, the third one, cyclopentanone. So you are getting this cyclopentyl magnesium, this one you are reacting it with acetaldehyde, you are getting a secondary alcohol. Now moving on to the tertiary one, you use cyclopentanone and benzyl magnesium bromide, and you are ending up with the tertiary alcohol. Now addition of alcohols. So addition of aldehydes and ketones react with alcohol in the presence of dry HCl gas. Now this HCl, it has to be dry. Okay, so dry HCl gas, you cannot use simply HCl because it will contain some amount of water, so you have to use HCl in its gaseous state and it has to be dry. Okay, so what you will get is gem dialkoxy compounds. Gem means geminal, dialkoxy means that is the two alkoxy group OR will be bonded to the same carbon atom, geminal. Okay, same carbon atom, geminal, different carbon means adjacent carbon atom, vicinal. Okay, geminal means same carbon atom, vicinal means adjacent carbon atom. So these gem dialkoxy compounds are also known as acetal or ketones, depending upon if you use aldehydes you will get acetal, if you use ketone you will get ketones. Okay, so first step is the addition of one molecule of alcohol to an aldehyde to give a hemiacetal. This one is the intermediate. Okay, hemiacetal, which contains both ether group and alcohol functional group. It is an unstable compound and reacts further with another molecule of alcohol to form stable acetal. Okay, now the reaction is reversible and therefore the acetals formed can be decomposed by dilute mineral acid to give back the original aldehyde. So this is the main reason that we have to use this dry HCl gas. Okay, if we do not use dry HCl gas, okay, then in the reaction mixture some amount of water will be present, that is dilute mineral acids. Okay, if you dilute HCl if we use dilute HCl, then it is a mineral acid, so it will revert back the reaction to the original aldehyde or ketone. Okay, so here it is the mechanism. So here you can see this one is the aldehyde. Okay, so after protonation, here this oxygen atom takes the proton. See here I am drawing. This oxygen has lone pair of electrons, means it has high electron density as compared to proton, which does not have any electron. Okay, proton does not have any electron, so it will share its lone pair of electron with the proton, so it will get protonated. This oxygen atom will bear a positive charge, so negative electronegative atoms bearing positive charge, now it will pull the pi bonded electrons more towards itself, thus making this carbonyl carbon more electrophilic in nature. Okay, now this carbonyl carbon making more electrophilic in nature, that means electrophilicity increases. Okay, so its reactivity increases. So now aldehyde, this alcohol, oxygen has lone pair of electrons. This lone pair of electrons will go and attack to this carbonyl carbon. So you are getting this OH from this one OH. This OH is there, and this ORH. Now hydrogen will leave. Okay, giving you hemiacetal. So hydrogen will leave and you will be left with hemiacetal. Okay, this one hemiacetal. Now these hemiacetals are very unstable compounds. So this hemiacetal, this hydroxy group of the hemiacetal will further get protonated, as here HCl is present, dry HCl is present in the reaction mixture. So this hydroxy group of the hemiacetal will get further protonated. So now this can leave as water molecule H2O. So what it will do, what this alkoxy group will do is that this alkoxy group with its lone pair of electron will donate electron to this carbonyl carbon, and this carbon will become pentavalent. Okay, see here that if we draw like this OR, this one hydrogen, this one alcohol, this OH. Okay, this one 2 plus this one. Okay, so see here this carbon is now pentavalent, so to maintain its tetravalency, this water molecule can leave with the bonded pair of electrons that will satisfy the positive charge of the oxygen atom in water molecule. Okay, so this H2O will leave. You can see here, oxygen will give its lone pair of electron, thus forming this oxygen carbon double bond. Since it will become, this carbon will become pentavalent, so oxygen bearing this positive charge will leave with this bond. This bond means, one bond means two electron pair, sorry, one bond means an electron pair, that is two electrons. So these two electrons will satisfy the octet of oxygen and it will neutralize this positive charge, and this molecule will leave as water molecule and you will get an oxonium ion. Okay, see here oxygen double bonded to carbon. Okay, now this oxonium ion will, we can see here this molecule is similar to this molecule, except in this place it is hydrogen atom, here it is an alkyl group. So it will undergo again 1,2 addition. 1,2 addition means, okay, if you are giving H and X, okay, this X minus, this is H plus, so one is going and attacking this one, so this is the first center, and the last one is getting added to this. oxygen, that is the second center. Okay, so this molecule, HX molecule, overall reaction is one atom and the second atom, means over two atoms the reaction is taking place, that is the addition reaction taking place over two atoms, so it is 1,2 addition. Okay, so it will undergo 1,2 addition, then this one, this molecule, it will get deprotonated to give you the acetal part. Okay, since here this oxygen atom bears a positive charge, so hydro proton will leave, and the this, let me zoom in. Okay, this oxygen atom bears a positive charge, so this hydrogen will leave as proton H plus, and this bond will satisfy the positive charge of the oxygen atom, giving you an acetal. Okay, so here we are using dry HCl gas. Okay, so it has two functions. First, it protonates the oxygen to increase the electrophilicity of carbon atom, and second, it absorbs the water produced in the reaction, driving the equilibrium towards forward reaction. See here, okay, in this step water is leaving, so if in this reaction water is there, so this water will mix up with dry HCl gas, and what you will be getting? Dilute mineral acids. So there will be a possibility to get back the original aldehyde. So to account for that, we are using dry HCl gas. Okay, so this water will be absorbed by this dry HCl gas, and thus in the water, in the reaction mixture, no water will be present. Okay, means here if water is present, then water will go and attack the carbonyl carbon again. Okay, see here, this is the carbonyl carbon in presence of HCl. Okay, this oxygen gets protonated. Now if water is present, then water will go and attack this one. Okay, and as I have shown you in my previous class, that this thiols, okay, this OH, similarly thiols or this acetals, means here in this one, this geminal hemiacetal, one diol is present. So these are very unstable compounds. So if water gets and attacks, sorry, my bad. See here, if what, sorry, forget about all those things. If in this hemiacetal, okay, if water is present, okay, so there is an equal probability that this hydroxy group or alkoxy group in presence of HCl will be protonated. Suppose if alkoxy protonates, okay, then what it will do is water will attack and this alkoxy group leaves. Okay, so you are getting a diol, and diols are very unstable. It will readily lose one water molecule to give you back the aldehyde. Okay, so if water is present, then it is very dangerous. So what HCl does is, this dry HCl takes up the water molecules. Okay, so now in the reaction mixture no water molecules is present, so you can have your acetal. Okay, that means here, see, you can see all the reactions are reversible. Okay, so in reversible means in equilibrium there is a forward reaction and an equal amount of backward reaction. So what dry HCl does is, it drives this equilibrium towards the forward direction. Okay, so now forward reaction is more, backward reaction is less. Okay, that is forward reaction more, backward reaction less. So this is the work of HCl. It drives the equilibrium towards the forward direction. So the reaction of aldehydes with dihydric alcohol. Dihydric means having two hydroxy groups. Okay, the alcohol having two hydroxy group, dihydric, okay, alcohol, such as ethane 1,2 diol or ethylene glycol, another name. Okay, it yields cyclic acetals. See here, these two carbon atoms are joined together. So in the product also, these two carbon atom will be joined together, and because of that we are getting cyclic acetals. Okay, see here, if you want a shortcut, then you know that in this reaction with alcohols, only water molecules leaves. So take two hydrogens from the hydroxy group of this diol and take this carbonyl oxygen. You remove one water molecule, and this oxygen you just connect it with carbon, and this oxygen you also connect it with carbon. So here see, you can see that this is the carbonyl carbon and these are the two oxygen atoms of the ethylene glycol. Okay, similarly cyclic ketals are formed when ketones react with dihydric alcohol. Okay, this one previously it was acetone, previously it was acetaldehyde, that is an aldehyde. Now this one is a ketone. Okay, you simply remove one water molecule like this as shown in the box, and you will get a cyclic ketal, also known as ethylene glycol ketal. Okay, and one water molecule. Now here one interesting reaction is there. Previously it was intermolecular. These reactions intermolecular, okay, means between two molecules. Intermolecular. Okay, but if the reaction is happening within the molecule itself, means in the same molecule, suppose this is the nucleophile. Okay, this is the long chain carbon, and here it is electrophile. That is, nucleophile is attacking the electrophile, but this nucleophile and electrophile are present within the molecule. Then it is known as intramolecular reactions. Okay, here you can see that this was the electrophile carbonyl carbon, and this hydroxy group is the nucleophile. These two molecules are different, not bonded with any chain. So reactions between two molecules, that is two different molecules, that is intermolecular. Okay, two or more molecules, but reaction within the same molecule, as you can see here, this one reaction within the same molecule, this nucleophile and this electrophile are present in the same molecule, then it is intramolecular. Intramolecular. Okay, these reactions are inter, and this reaction is intramolecular. Okay, see here, uh, now this one is the aldehyde group and this one is the hydroxy group. So this one alcohol, this one aldehyde. So this hydroxy group can go and attack this carbonyl carbon, and this pi bonded electrons will go to oxygen and it will take proton from the solvent. So you are getting cyclic intramolecular hemiacetal. Okay, so now what is the use of this reaction? So one use is that you can see here, this is used in the protection of carbonyl compounds. So this is one compound. If you treat it with lithium aluminum hydride, so you can see here this has a ketone group and one ester group. So both ketonic group and ester groups are reduced to alcohols. You can see ketones reduced to secondary alcohols and ester reduced to primary alcohols. But if we use this dihydric alcohol, okay, so what it will do is it will just capture or rather protect the carbonyl group by forming a cyclic ketal. Then further reduction with lithium aluminum hydride, this will remain as it is, because lithium aluminum hydride does not react with this cyclic ketal or acetals. But what lithium aluminum hydride will do is it will reduce this ester to primary alcohol. Okay, so we are selectively reducing ester in presence of a ketone. We know that ketones are much more reactive than esters. Okay, so what we are doing is we are selectively reducing a less reactive functional group in the presence of a more reactive functional group. That is the selective reduction. Okay, further, this deprotection using mineral acid will give us our ketonic group back. So you can see here in the final compound, compare it. Now this is our final compound, compare it with the unprotected one. So you can see here that we are selectively reducing esters to alcohol. In this one, where we are not using the cyclic ketone, we are getting two reduced products, but in this one we are getting only one reduced product. Okay, so this is the advantage for protection. So now, like alcohols, thiols means thioalcohols. Alcohols means OH. Okay, thiols means SH. Okay, like alcohols, thiols reacts with aldehydes and ketones to give mercaptan, a dithiol acetal derived from an aldehyde, which on further oxidation gives sulfones. So this is the structure of sulfone. So here is the aldehyde and this one is the ketone. So instead of alcohol we are using thioalcohol. Same mechanism, everything same, except instead of OH we are getting instead of OR, okay, we are getting SR, that is mercaptan. We are getting mercaptan, not acetal or ketal, mercaptan. Okay, similarly here you can see instead of OR we are getting SR. Further oxidation of this SR will give you sulfone, SO2R, and this is the sulfone structure. Okay, here this R is this group. Okay, this group. So and the next SO2R, this S double this two oxygen and this R, SO2R. Okay, this is the sulfone. These are the sulfone compounds. Okay, now this portion is very important for both your normal board exams and for entrance exam. Okay, this one, reaction with ammonia derivatives, and also reaction with ammonia. I will come onto that later. So aldehydes and ketones reacts with a number of ammonia derivatives. So ammonia is NH3. Okay, NH3. If we replace one hydrogen of ammonia with any functional group or any other group, normal alkane also, then we will get is a derivative of ammonia, that is here NH2. Okay, you replace this hydrogen with any other group, suppose R, then we will get RNH2. So we are substituting this hydrogen with an alkyl group. So this compound, this RNH2, R could be anything. Okay, RNH2 is the ammonia derivative. Okay, so aldehydes and ketones react with a number of ammonia derivatives in weakly acidic medium to form compounds containing CN double bonds. Okay, this is important, CN double bonds with elimination of water molecule. The reaction is reversible and is catalyzed by acid. We are doing it in weakly acidic medium, so it is catalyzed by acid. The equilibrium favor the product formation due to rapid dehydration of the intermediate. Okay, now let me explain this. So first, this one is the carbonyl compound. Okay, and adjacent to it is the ammonia derivative. So this will react first, this in weakly acidic medium catalyzed by acid. This carbonyl oxygen will get protonated, then further nucleophilic addition of nitrogen to the carbonyl carbon will take place, okay, giving you this intermediate. Now you can see here that this nitrogen contains a hydrogen atom, and here it is hydroxy group. So what it will do is it will lose one water molecule. So this bond goes over here and this will leave. So one water molecule it will lose and forms carbon nitrogen double bond, okay, and here Z is the substituent, okay. This could be alkyl, aryl, OH, NH2, C6H5NH, etc, etc, okay. This is the derivative of ammonia. So in short, you can see here that you just need to remove one molecule of water, just like the previous one here, just like this one. You have to remove this water molecule. Here also same, you just remove this water molecule and you will get your final product, okay. So here you can see the mechanism. First, this carbonyl group is activated or rather catalyzed by this proton. So we have to use it in weakly acidic media, that is catalyzed by acid. So these are the canonical structures, okay, that is the resonance structure of the carbonyl group. So now this carbonyl carbon will get activated. Now nitrogen will go and attack, sorry my bad. Now this nitrogen atom will go and attack this carbonyl carbon. This will go over oxygen, this bond. So you are getting this product, okay. Now proton transfer from nitrogen to oxygen atom. Now this nitrogen bears a positive charge. So oxygen is more electronegative. So it has electrons. So it can take one proton from nitrogen. Okay, it will take and become OH2 plus. So now this nitrogen will be neutral. Now moreover, this nitrogen also has one hydrogen atom, okay. So what it will do is it will leave hydrogen atom, this will go as water molecule. Or if you want to see here, if you want to visualize, then you see here this water molecule leaves, okay. This water molecule leaves forming a carbocation, okay, and this is the resonance structure, okay, canonical structure. So if we consider this one, okay, here nitrogen has a positive charge. You can see here nitrogen has a positive charge, so the proton will leave, leaving a neutral compound, okay. So this is the mechanism, or simply you can just remove one water molecule to get the final compound, okay. So what are these final products called, okay. So if Z is hydrogen, then this reagent name, this is the reagent, okay, this is the reagent name, and this will be the product name, okay. So if Z is hydrogen, it is ammonia, and the carbonyl compound derivative you will get this one, okay, and it is known as imine. If it is R, then the reagent is amine and this is substituted imine, that is a Schiff base, okay, Schiff base, you remember this one name, it comes in entrance exam, okay, Schiff base. If it is OH, then it is the reagent is hydroxyl amine and you are getting oxime, see here OH, okay, NOH, then NNH2, it is hydrazone, then NNH phenyl hydrazone, and this one, this is very important for your both boards and your entrance exam, okay. 2,4-dinitrophenyl hydrazone, okay, this I will talk about later. and this one is, if it is NHCONH2, this is semi-carbazide, and this is semi-carbazone. You are getting the product. Note here is that, see here only this Z is different. Okay, here it is H, here it is R, OH, NH2, NHPH, and this is substituted one, this is NHCO, NH2. Rest are the this two alkyl groups, then carbon double bond nitrogen are same in all the products. Okay, these are same in all the products, only the difference is this Z. Okay, it is only the difference is this Z. Okay, this Z is the difference. So now the reaction is pH dependent and takes place at pH 4 to 4. In some book it is written 3 to 4. Okay, oh sorry, here it is 4 to 5. In some book it is written 3 to 4. Okay, so why you have to maintain a certain pH? Why is it so? Okay, this one is also very important for your entrance exam. Questions comes over this. Okay, they are giving some reagents and they are asking which reagent will not give you the product. Okay, they will, of course they will give some conditions over there. While solving the questions, we'll discuss this one also later in later classes. Okay, so when pH is very low, okay, that is highly acidic medium, so the ammonia derivatives being basic in nature from their respective ammonia salts consequently lose their nucleophilic nature. So this one is a ammonia derivative. Here we have replaced hydrogen with methyl group, so it is methylamine. Okay, so in strong acidic medium, this nitrogen has lone pair of electrons, so it will coordinate with proton. Okay, and this will leave as chloride ion. So what we are getting is methyl ammonium chloride, ammonium salt. Okay, see here, that's this is the positive portion and its counter ion chloride minus. Now nitrogen, now for this step, okay, we need lone pairs of electrons in the derivative, ammonia derivative. Okay, but this, in strong acidic medium, this lone pairs gets coordinated to a proton to give ammonium salt. So now nitrogen is devoid of any lone pair of electrons, so it cannot take part in the reaction and thus this reaction will not take place. Okay, what if the pH is high, that is in basic conditions? So at higher pH the carbonyl group will not be sufficiently protonated. That is, if we see here, this protonation and this activation of carbonyl group, that is the increase in electrophilicity of carbonyl carbon, takes place in weakly acidic medium. Okay, but if we incorporate weakly basic or basic medium, so this activation won't take place and as a result further reaction will not occur. Okay, so you can see that if the reaction medium is strongly acidic, then second step will not occur and thus rest other steps will not take place. And if the reaction medium is weakly basic or strongly basic, then this first step will not occur and thus in both the cases, that is if the pH is high or if the pH is very low, then we will not get any final product, that is the reaction will not take place. So the reaction is pH dependent and we have to maintain certain pH values, that is 4 to 5 or 3 to 4. In some books it is written. Okay, so now I was talking about this one, 2,4-dinitrophenyl hydrazone. Okay, the final product and the reagent is 2,4-dinitrophenyl hydrazine. Okay, so this is the 2,4-DNP test. Okay, so if you want to confirm your carbonyl compound, what is a carbonyl compound in organic analysis, salt analysis? So this one is the test done to identify the carbonyl compound. So your carbonyl compound is given, you just do the 2,4-DNP test, you will get your final product and you record its melting point, and all other aldehydes, this final product, all other aldehydes and ketones, this final product, that is the hydrazone product of all other aldehydes and ketones melting point, are recorded in a literature, and you just have to match your melting point with the one that is recorded in the literature. Okay, so aldehydes and ketones react with 2,4-dinitrophenylhydrazine. So this group is hydrazine. Okay, NH2 NH2. This group is hydrazine. If we remove one hydrogen, okay, one hydrogen with this 2,4-dinitrophenyl, okay. So here see, this one is 1, this one is 2, this one is 3, and this one is 4. So 2,4-dinitro. So if we replace one hydrogen with 2,4-dinitro, so what we are getting is 2,4-dinitrophenylhydrazine. Okay. So aldehydes and ketones react with 2,4-dinitrophenylhydrazine to form yellow, orange or red PPT. This reaction is used for distinction of aldehydes and ketones. So among the carbonyl compounds, you will get to know what is your actual aldehyde or ketone. That is, it is whether it is acetaldehyde or whether it is propanal, butanal, or whether it is a ketone, that is acetone or benzophenone. So you will get to know, okay, exactly what your carbonyl compound is, and this is known as 2,4-DNP test, or rather Brady's test. Okay, you have to know this name, this Brady's test. Okay, so you just see here acetaldehyde, you just replace this, you just remove water and you will get ethanol 2,4-dinitrophenylhydrazone. Here you are getting hydrazone. From hydrazine you are getting hydrazone, okay, and a water molecule. So this is your final compound, hydrazone. So aliphatic aldehydes and ketones give yellow PPT with 2,4-dinitrophenylhydrazine. See here, aliphatic, okay, aliphatic gives you yellow PPT, and similarly if it is aromatic, okay, you will be getting a red PPT. That one is aliphatic, yellow or yellow orange type, and with aromatic you are getting a red PPT. See here, this one acetophenone, okay, here phenyl group means an aromatic portion, this one aromatic portion. So acetophenone 2,4-dinitrophenylhydrazone and a water molecule. So aromatic aldehydes and ketones, you are getting red PPT. Okay, so I have discussed the reactions of carbonyl carbon with ammonia derivatives. Okay, so now why I have not mentioned ammonia also, why I am mentioning ammonia as another topic, not included in the ammonia derivatives. Okay, now you will get to know reaction with ammonia. See here, aldehydes except formaldehyde, okay, this formaldehyde except formaldehyde, it will react with ammonia to form aldehyde ammonia adducts, which on warming with water decomposes to give imine. Okay, so you can see here that this one acetaldimine, okay, so you can see here you are getting the same kind of product, but here nitrogen is substituted. Okay, and here nitrogen is not substituted, it is NH, but here an extra step is that you have to warm this one with water. Okay, whereas in the previous this you do not have to do anything, it will just simply give you the final product, whereas here you are getting acetaldehyde ammonia adduct, and on further warming with water you are getting this acetaldehyde. Okay, so acetaldehyde, ammonia is just ammonia will go over here and this will open up. You are getting this acetaldehyde ammonia adduct. I just shown you like this only. Okay, just remember like this. Don't have to go for details. Okay, for every reaction, if you go into details, then you will mug up all those things. Okay, so acetaldehyde ammonia, you are getting adduct, ammonia adduct. Okay, and further warming with water, you are getting acetaldehyde. Sorry, acetaldehyde. Okay. Now, what about formaldehyde? Now, this reaction is important for your both boards and entrance exam. Okay. So, formaldehyde reacts with ammonia to form hexamethylene tetraamine, that is hexaamine, also known as hexaamine. This is the formula of hexaamine. Okay. CH2 whole 6 N4, and this is also known as urotropin or methanamine. Okay. It is used as a medicine to treat urinary infections. Okay. So what is the reaction? This is the reaction. Okay. Similarly, formaldehyde, it will react with ammonia to give you the same adduct, which if you heat will give you formaldehyde and water. But this formaldehyde is very reactive. Okay. Unlike this aldehyde. Okay. This aldehyde, you are getting one ammonia adduct and further warming it decomposes to acetaldehyde. Okay, here also same, you are getting ammonia adduct, on further warming you are getting formaldehyde. But here this formaldehyde, unlike this acetaldehyde, this formaldehyde is very reactive and it reacts further with ammonia to give you urotropin. Okay, CH2 whole 6 N4, urotropin. So this is the structure of urotropin. Okay, this is the two-dimensional structure of urotropin. Okay, two-dimensional. So how is this what is the balanced reaction? See here, 4 molecules of ammonia and 6 molecules of acetaldehyde. As from its formula, you can see here that CH2 whole 6. As from the formula, you can see CH2 whole 6 N4 means 6 carbon atoms and 4 nitrogen atoms. So in formaldehyde there is only one carbon and in ammonia there is one nitrogen. So obviously you have to take 4 nitrogen to get N4, and to get CH2 whole 6 you have to take 6 molecules. Okay, so 6 molecules of formaldehyde will react with 4 molecules of ammonia, releasing 6 molecules of water and urotropin. So that one was the 2D structure, and this is kind of a 3D type. Exactly not 3D, this one was also like 2D, but it's the proper orientation of the bonds. Okay, here you cannot say these carbons as uh, I mean to say that the geometry of the molecule, here the geometry is shown. Okay, this is the geometry of urotropin, this is the actual structure of urotropin. Okay, so and this one is a very interesting reaction. Okay, so nitration of urotropin, nitration. Okay, nitration of the urotropin under controlled conditions, we will get RDX, that is the explosive. So what is the full form of RDX? Research and development explosive. Okay, so see here, hexamethylene tetraamine, that is urotropin, you nitrate this one. Okay, under controlled reaction. Okay, see, controlled reaction, because it is very explosive in nature. Okay, so you have to control the reaction. So what you will get is RDX, or another name is cyclonite or cyclotrimethylene trinitramine. Okay, cyclotrimethylene trinitramine, along with 3 molecules of acetaldehyde and an ammonia molecule. See here what happens. This nitrogen, this nitrogen and this nitrogen, these 3 nitrogens get nitrated, okay, and this bond cleaves, the bonds inside this 6-membered ring get cleaves, giving you 3 molecules of acetaldehyde and 1 ammonia molecule. Okay. So we talked about formaldehyde and other aldehydes except formaldehyde. What about ketones? Okay, so acetone reacts with ammonia to form diacetone amine. So first acetone reacts with ammonia. You are getting this same adduct as you were getting in acetaldehyde and this formaldehyde. You are getting same adduct, but this adduct further reacts with another molecule of acetone, and what happens here? This water molecule goes out, and what you are getting is diacetone amine. Okay, diacetone means 2 molecules of acetone and 1 molecule of amine goes and form this compound. Okay, so this portion is from first molecule of acetone and this one is from the second molecule of acetone, and this is your amine. Okay, so what is the name? Its name is 4-amino 4-methyl pentane 2-on, that is diacetone amine. So if you want to means remember in short, okay, for acetone you just take one hydrogen from the alpha carbon. Since this one is the functional group, so this carbon is alpha carbon, this alpha carbon is alpha carbon. So you take one hydrogen from alpha carbon, one hydrogen from ammonia, and the oxygen from another molecule of acetone. You just remove one water molecule, you will get diacetone ammonia or diacetone amine. Okay, simply this, just shortcut if you want to remember like this. Similarly, benzaldehydes react with ammonia to form hydrobenjamide. Okay, same kind here. You take one oxygen, here you take 2 hydrogen from ammonia, 1 oxygen 2 hydrogen, and the rest 1 hydrogen, it will go and react with this another molecule of benzaldehyde, and here also 1 hydrogen with this oxygen. So here you are getting 3 molecules of water and the rest is hydrobenjamide. Okay, so see here, this kind of reactions mechanism is very lengthy. Okay, so you have to memorize it like this. Okay, if you want to go details into the mechanism, if you want to know the detail, then okay, I will let you know, but you have to tell me. But these things are for your colleges. Okay, when you will be in your degree, that is when you will be doing BSc, so you will get to know about the mechanisms. Okay, these are the just the shortcuts you have to remember. Okay, for for doing this kind of reaction efficiently, means within some few seconds, say 5 or 6 seconds, you know, just this reaction. If entrance exam you are getting, in entrance exam you will get around 4 seconds for per question. Okay, if the paper is too long. Okay, 4 to 5 seconds, or in some entrance exams rather a minute. So you cannot lose your precious time. So what you have to do is you have to remember these steps. You just remove water molecule and you get the final product. At last, if you are getting the right answer, that counts. Okay, so now reaction with sodium alkynide. So what are sodium alkynide? It is nothing, just the alkynic derivative of sodium. Okay, see here, sodium is always positive charge, so this one will be negative charge. If we see acetylene, okay, this is one, this is acetylene. So these protons are acidic in nature. These are acid acidic in nature. Why? Because this one is sp carbon, sp hybridized carbon. Okay, this one sp hybridized carbon, and the hydrogen attached to sp hybridized carbon are acidic. Okay, so if you give any, what do you call, any base, it will give you this one. Okay, so this one is sodium alkynide. So if we treat carbonyl compound with sodium alkynide, what it will do is this negative charge will go and attack the positive carbonyl carbon. This one will go towards oxygen. So this one you are getting as intermediate. Further acidic hydrolysis, and you will end up with OH here. Okay, this ONA, that is ONA, that is O minus Na plus. This O minus now will take proton from water molecule to give you this OH, that is this OH. Okay, so here is an example. So first you treat it with sodium alkynide. So if we treat it with sodium alkynide, what we will get is this CH3, then C, this one O Na, this is C3H7, and this one is C triple bond CH. Okay, now second step is hydrogen nickel, means reduction. So this H2 nickel will reduce this alkyne part to alkane. So in hydrogens we know that for per single bond we are adding 2 hydrogen. Okay, per single bond 2 hydrogen. So here we are reducing 2 bond. So we will be adding 4 hydrogen atoms. Okay, 4 hydrogen atoms. So see here in the product, here 2 carbon, so C2, 1 hydrogen, and here 4 hydrogen atoms we added, sorry, 2 carbon atoms and 1 hydrogen atom, that is C2H was present. Now after reducing we are adding 4 hydrogen atoms, that is H plus 4 hydrogen atoms give you H5, so C2H5, and after that dilute HCl, it will convert ONA to OH. Okay, so now next reaction with water. So water attacks the carbonyl group of aldehydes and ketones. The transformation can be catalyzed either by acid or by base and leads to equilibration with corresponding geminal diol, also known as carbonyl hydrates. I have shown you this reaction, okay, in the reactivity of carbonyl lecture. Okay, I will give a link in the top right corner of the video. You can check from there this reaction with water, the mechanisms of the reactions with water. I'll give in the top right corner. I'll share one link. Okay, now carbonyl hydrates. So this is neutral condition. Carbonyl will react with water molecule, same, and you will get unstable hydrate. Okay, that is the geminal diol. Unstable hydrate, it has a tendency to go back to revert back to this carbonyl, original carbonyl compound. Okay, so now what is most interesting is that few carbonyl groups are there which does not give a reversible reaction with water. That is, the equilibrium, it does not remain in equilibrium with the hydrate. That is, for those carbonyl groups, the hydrate, this unstable hydrate molecule is actually rather stable. So what are those carbonyl molecules? So this comes in entrance exams a lot. Okay, so first one is chloral. Okay, see here, this has a carbonyl group, it reacts with water to give you chloral hydrate. Now here it is a remarkable property of this compound is this hydroxy hydrogen is being hydrogen bonded. Okay, it is being hydrogen bonded to this Cl group, that is the chlorine group. See, chlorines have higher electronegativity than carbon. So chloride, that is the Cl, will bear a negative charge, and due to the electronegative nature of oxygen, this hydroxy hydrogen will have a positive charge. Okay, del plus, infinitesimally positive charge. Okay, so del minus del plus, so this can hydrogen bond. Okay, that is the hydrogen atom and chloride atom can hydrogen bond among each other. So here you can see that this chloral hydrate actually hydrogen bonded. Okay, this is the first hydrogen bond and this one is the second hydrogen bond. So this one is, this hydrogen bond is within the molecule. Okay, see here, this negative center and this positive center, these two centers are within the molecule. So this hydrogen bonding is known as intramolecular bonding. Okay, intramolecular hydrogen bonding, that is the bond hydrogen bonding if occurring within the molecule, then it is intramolecular. So here you see that intramolecular hydrogen bonding. Okay, so this one is the first intramolecular hydrogen bonding and this one is the second intramolecular hydrogen bonding. So chloral hydrate have two intramolecular hydrogen bonding. Sometimes it may ask that how many hydrogen bonding does chloral hydrate give, or among this, or another question is there. Okay, they will give a bunch of aldehyde among which you have to uh, check which molecule reacts with water. Okay, so those molecule those normal carbonyl group will not react, means they are asking for a stable hydrate. Okay, not an unstable hydrate. Every carbonyl molecule will react, but in that question they are not mentioning, but they are literally asking for a stable hydrate. Okay, that is stable hydrate. Similarly, you see this is the final compound. Okay, 2,2-dihydroxy 1H indene 13H dione. This is ninhydrin. Okay, this is the IUPAC name. Okay, you just have to see that if you see this kind of molecule, you see that this OH group and this carbonyl group has carbonyl oxygen del minus, OH hydrogen del plus. So intramolecular hydrogen bonding. Similarly here also intramolecular hydrogen bonding. So that intramolecular hydrogen bonding is also present in this molecule, that is 2 intramolecular hydrogen bonding. So these two compounds does not give reversible reactions with water. There are many more compounds, but you have to look like this. Okay, if there is this hydroxy, you have to look for the hydrate. Okay, here there is hydroxy groups. So now whether if any substituent is present in the alpha carbon, that is this one is alpha carbon, if any substituent is present in alpha carbon of the carbonyl group, not of the hydrate. Okay, this alpha carbon is from the, sorry, see here, this one is alpha carbon. Okay, this one is alpha carbon in the sense it is alpha to carbonyl group. Okay, if the substituent of alpha carbon bears a negative charge, then it will hydrogen bond with the hydroxy hydrogen atom. Okay, similarly here you can see that this one, if you consider this as the alpha carbon, okay, this alpha carbon has O minus as substituent, so this can bond with hydroxy OH, sorry, hydroxy proton. Okay, you have to look for substituent in alpha carbon. Okay, now reaction with phosphorus pentachloride, that is PCl5. Okay, When aldehydes or ketones react with PCl5, they form gem dihalides. Gem dihalides means the dihalide on the same carbon atom. So gem dihalide, geminal dihalides. So acetaldehyde PCl5, you are getting this. You replace, see here, this is one. You just replace this double bonded oxygen with two halide groups. Okay, this is the final product. Similarly, acetone PCl5, just replace this oxygen atom with two chloride. This is the reaction mechanism. Here's all of this. Okay, see here, as usual. Okay, oxygen del minus and this one del plus. Okay, now PCl5. Okay, now this negative center will attack this phosphorus, and phosphorus is now here pentavalent, so it will leave one chloride ion. Okay, so you will get this molecule. See here, this phosphorus contains 4 chloride ion bonded chlorine molecules, and this one is free. Okay, because this one leaves. So this bond actually goes and attacks here. Okay, you can show here resonance, then if you want to show the resonance structure, this will go here and this will give like this. Oxygen here, oxygen will be a positive charge, then PCl4. Okay, then this bond will come over oxygen to satisfy its positive charge, and you will get here carbon as positive charge. Now this carbon bears a positive charge, so chloride ion will attack this carbon atom. You will get this one. Okay, here see, this chloride is it's attached with this carbon atom. So now you see that phosphorus has a very good affinity for oxygen. Okay, so it will take this bond and forms a double bond here, and one chloride ion will leave. Okay, so we are getting another free chloride ion and this carbon as positive, because oxygen is taking this bond and forming double bond in with phosphorus. Okay, oxygen taking this bond, that is, I will show. So, see here, oxygen is taking this bond and forming a double bond here with phosphorus and expelling one chloride ion. So this free chloride ion, here it is, and this carbon will bear a positive charge again, so this chloride ion will go and attack this positive carbocation, forming the final compound. This, see, oxygen has a very good affinity for phosphorus, so in first place this oxygen goes and attacks this phosphorus. Okay, PO bond is very stable, so as a result of which, in the first place, oxygen goes and attack peace. Oxygen go and attack phosphorus. Okay, and secondly, here oxygen takes this bond to form P double bond O, because oxygen has a very good affinity for phosphorus. Okay, so this is how it will go. So now I have completed the nucleophilic addition reaction. In the next lecture videos, I will be discussing about oxidation and reduction reactions of those carbonyl compounds, means how reagents will go and react oxidatively or reductively with those carbonyl compounds. Then we will be discussing some miscellaneous reactions along with some name reactions. Moreover, there are many name reactions, I think 6 to 7 name reactions, which are very important for your entrance exams. It is not included in your board syllabus, but it is important for your entrance exam. So if you want me to discuss those name reactions also, those reactions for your entrance exams, so please comment below that you want to learn those name reactions apart from your board syllabus. Okay, so or just let me know, just let me inform that you need those reactions. I will also make a video on that. Okay, so if you have any queries regarding this lecture video, so you can comment down below. As you know, I am not getting that whether you are able to understand this, whether you can grasp all these things, whether you are fully understanding what I am saying. So I am not knowing any of these things, so please let me know whether if any queries are there or any doubts. Please mention it in the comments below. Thank you.